Hey everybody, I'm Sam and this is the Entiversal machine learning tutorial where we explore the world of AI together and learn not only the theory but also implementation by going through cool examples step by step. Today we will be talking about the Perceptron. This will be the first episode from a long series on neural networks where we will move from the perceptron and artificial neuron to deep neural networks and hopefully get into some convolutional neural networks, recurrent neural networks, and reinforcement learning. So I will start with introduction on biological neurons and some history on the very early days of machine learning. Then we will get into the theory behind the perceptron, and finally we will go through a simple example on paper that will show us step by step the perceptron algorithm. Okay, as I mentioned, a bit of introduction on biological neurons. As you probably know, the human nervous system is architectured by single cells called neurons. As you can see on the figure, a typical biological neuron is comprised of a cell body, tentacle-like dendrites, which are the input channels of the cell, and the axon, which is the output channel of the neuron. There usually are a high number of dendrites as well as the axon branches, so you can see how a single neuron can connect to many others, forming a complicated network. So to each of the dendrites you can have input neurons, right? And to each of the branches of the axon you can have other neurons which would take an input of our neuron here. So I will not get into the chemical processes of how the biological neuron works. Maybe we will do that in a separate video, but let's look at its functionality. As we mentioned, to the dendrites, the neuron takes inputs from other neurons. If the neuron becomes sufficiently excited, it responds, fires by sending an electric pulse output to the axon. And here we can see an animation of that, how the pulse comes in and then if it's excited goes out. And here is another one of the impulse going out. This is the axons, the dendrites of our neuron. It excites and then it goes out. The output travels down each branch, providing an input to the connected neurons and so influences their behavior. The biological neuron follows the all or none rule, meaning that it either fires or it does not. There is not weak or strong firing. Instead, when the neuron is more excited, it fires more rapidly. So now it becomes clearer that neurons take inputs from other neurons, and based on their value and some kind of internal rule of when the neuron gets excited, it could fire or not, consequentially exciting other neurons in the network. So after gaining insight into how the biological neuron operates, people started thinking on how to represent that in a mathematical model. The simplest model is just an addition of the inputs, right? So here we can see that we just add x1x up to xm, and the output is just the sum of those inputs. However, there are some problems with this representation because since the x's or inputs will always be positive, the mathematical neuron would always fire, instead of having a rule of when it is excited enough to fire. Also, if the number of inputs, the connected neuron axons, are big, the output would be huge, right? The value of the output. And we said that the biological neuron has an upper bound of the pulse strength, right? It's either weak or strong, but it can't just vary and be infinite. So in order to fix the problem of continuous firing, a threshold called bias was added. It's a very important thing. We'll be hearing a lot about bias in the future. So Now the neuron would fire only if the sum of inputs is high enough to outweigh the bias or this threshold, and then we'll get a positive value and we will fire. This is great. However, a problem still remains, that the inputs can only excite the model but cannot inhibit its operation, right? Because it's still always a positive value. So in order to model both excitation and inhibition, multipliers of the inputs called synaptic weights were introduced. Each input is weighted by its synaptic weight, while the bias is just multiplied by 1. After adding them together, we get what is called the weighted sum of inputs, which in our case is the output. Other names for it are net activation, some people call it induced field. And now we can apply weights which could be both positive or negative, and in this way we can either excite here, so have a positive value, or inhibit by having a 0 value or a negative value. Okay, so at this point a single problem remains. The output will still be huge if there are many inputs or the weights are big, right? If we have just positive weights and we have a lot of inputs, our output here, since it's a sum, will be huge. This is where Warren McCulloch, who was a neuroscientist, and Walter Pitts, a logician, come in. They are credited for coming up with the first computational model of the artificial neuron back in 1943. They added a threshold which is implemented through a step function, reflecting the internal rule or function of the biological neuron. Now the model outputs only 0 or 1, depending on if the net activation is higher than a certain threshold, which usually is chosen to be 0. The McCulloch neuron is quite close representation to the biological neuron functionality because it always obeys the all or none rule. Now, depending on the value, if it's greater than 0, we get a 1, and if it is less than 0, the weighted sum of inputs or net activation, we get a 0. At this point, we already finished the introduction to the biological neuron and came up with a quite accurate mathematical model of the artificial neuron. It is time to start looking at things more from the machine learning perspective. So, what is the point of having the said model? What do we want it to do? Well, the output could be either 0 or 1, depending on the inputs. That means that the model might be able to classify between two different classes of things, or in other words, to be a binary classifier. If that is the case, the weights will be determining the slope of our decision line or boundary between the classes, while the bias term will be shifting the decision boundary with respect to the origin. Well, this is fantastic, but how do we make the algorithm classify things? Well, we need to learn a model, right? From now on, when I say model, I would be referring to the weights and bias values. Or in other words, we need an algorithm which modifies the weights and bias until we get an accurate classification, and here on our output we get 0 for all the samples which are from class 0 and 1 from all the samples which are class 1. Well, what do you know? We're in luck, because back in 1958 Frank Rosenbaum came up with the Perceptron algorithm. The algorithm initializes the weights to random small numbers, which could be positive or negative, usually in the interval between minus 0.1 to 0.1 and the bias to 0. Then it starts computing the output of the model for each input sample. After getting the output, the model would be updated based on the difference between the target output, also called true label, and the output we got from the current model, multiplied by the input sample and scaled by a constant called the learning rate, which represents how fast we want to modify the model. The training, or also called learning, continues for a set number of iterations or until all outputs are correct, which we call convergence. Okay, now let's look at some terms that all of us need to know and understand in order to understand better when all of those machine learning guys are talking around us. So we have net activation, we already mentioned that. This is the sum of all inputs multiplied by their respective weights and added with the bias. Activation function is a function applied to the net activation, transforming it into the model output. Forward pass is getting the model output, right? We have an input, we make the forward pass, we get the output. Inference is when we perform forward pass, but the model is already learned, which means that we do not update, because first we have the training period when we train our model, and then when we have learned it, which means we give it some input and we want to see what we'll get as an output. Target or true label, this is the output we want the model to learn, to compute. Loss or error, this is the difference between the target and our model's current output. Backward pass, this is calculating the loss, or we'll see in future tutorials the gradients, but let's just think it as the loss. Learning rate, this is the rate of change of the model when we update it. Update, this is the term we use to update the model. It is multiplication of the learning rate, the loss, and the input. Epoch, this is going through all the training input samples. For example, if we have 3 input samples and we go through each of them and we do our backward pass, that means we have done a full epoch, and we'll see more about that in the example in a bit, and it will be even more clear. Convergence is the moment when the model has learned and the loss is minimized. This is basically the best performance we can get from our model. Okay, that is all great, but you're probably wondering, why does the Perceptron learning algorithm work? After all, we are just subtracting the update term from the weights, and we do that time after time when our model is wrong. But what does that represent? Let's think about what we are trying to achieve. We want to minimize the loss, right? We are trying to get convergence. Or in other words, we want to move our model in the direction where the loss decreases. So if you're looking at the picture now, if what we have plotted here is our loss, and here the z-axis is our loss, and it depends on x and y, which could be our model output and the true target label, let's say. We want to move from a place where we have a lot of loss to the place where the loss is the smallest. Here is the point of convergence. But with the update of the weights, we penalize the loss, right? We subtract, which is exactly what we want to do, and we scale it by the value of the input. But why do we want to scale it by the value of the input, right? Quite logical question. Well, if we step back into the biological neuron world again, a big input would represent a lot of input neurons firing together. A small input would represent only a single or a few of the connected neurons firing. If the input is small, the loss would be with respect to only a few of the connected neurons. If the input is big and we have a loss, the loss would be with respect to many or all neurons. We do not want to change our response much based on only a small portion of what is driving us, right? However, if everything is firing and we want a loss, we want to change a lot our model, so we move to a better place. Also, if a particular neuron is not firing, then the loss, as we said, is not with respect to it. So why would we want to update our model with respect to that neuron, right? But if we have that the neuron input is 0 and we multiply it by the loss, then we just erase the loss and we don't change the weight or the parameter of this particular neuron. The learning rate tells the algorithm how fast we want to go towards the minimum of loss. This is important since going too slowly takes time, right? But going too fast might make us miss the target. So the learning rate should be tuned carefully. It usually has values of 1 to 0.01, mostly around 0.1, but it is kind of trial and error thing, and the time when we try to get the best learning rate is usually called validation. Okay, so we now not only have the mathematical model, but also the algorithm, which we can use to teach it to do useful stuff. The question is though, what kind of classes can the perceptron classify? Since the net activation is linear, if you have watched my linear regression video, it would be very familiar. The step function is also linear. That means that the patterns that we are to classify need to be linearly separable. And here I have made a little picture of what linearly separable means. Even though that they are the same classes, if they are spaced into the data space in such a way that they are not linearly separable, that means that we cannot use the single perceptron to classify between them. And we'll see more about that in the next tutorial when we run some really cool experiments on that. Okay, so for a simpler example, let's consider the AND, OR, and XOR logical functions, where AND and OR are linearly separable. As you can see, we can drive a single line between the ones and the zeros, and XOR is not. We cannot drive a single line between the class 1 and the class 0. In the next tutorial, as I mentioned, we'll look at Perceptron in Python implementation that I made, and we will see that while the Perceptron can learn AND on OR or even quite more complicated functions, we cannot learn XOR. Okay, let's do a super simple example. This is the truth table of the AND logical function, which, as we said, is linearly separable. And let's train a model, a perceptron, which can fit it. Since we have two inputs, we can call them features. We need two weights and one bias. Let's say that initial values of weight 1 and 2 is 0.1 and the bias is 0. We will use learning rate of 0.5. Now let's skim through step by step to this example and really see how the perceptron algorithm works. Okay, so this is the formula of the forward pass or the forward step, as we mentioned. So here we have our net activation, which is because we have two weights, weight 1, weight 2 multiplied by x1 and x2. We add our bias and we take the step or function or threshold, right? Our threshold will be 0, and then we get our output. And the output we get, we want to be the x and x2, while x1 and x2 will be our inputs. Here I have also shown the update rule. The new weight is equal to the current value of the weight minus learning rate which we said we'll use 0.5 multiplied by the output minus target multiplied by x, or the input. And by the way, when I say input here, I mean the input which is associated with the particular weight. Okay, so let's train our perceptron, shall we? Here we begin epoch 0, and the first sample, as we saw, is 0, 0. We do a forward pass, 0.1 multiplied by 0 plus 0.1 multiplied by 0 plus 0 is 0, which the step function will read as 0, and our target is 0, so that's why I made it green here, because we classified it properly, so we don't need to update anything. The next training sample is 0, 1. We do the forward pass, we get 0.1, which will be translated into 1, right? Because our threshold is 0. But our target is 0, so we have to update. We update 1, we don't update actually anything because the x is 0, right? So the loss with respect to the first weight is nothing basically, so it stays the same. We do update the second weight though, and we get minus 0.4, and we update the bias, which is 0, which is the current bias, minus 0.5, the learning rate, multiplied by 1, which is the output of the perceptron, minus 0, which is our target, multiplied by 1, which is the multiplier of the bias. It's always 1, and we get minus 0.5. Okay, great stuff. Then we do the third input sample, which is 1, 0. We get as a net activation minus 0.4, which is translated into 0 as an output. Our target is 0, so we are set. We have 1, 1. We get 0 as output, but we want 1. So now we update, and our new values are 0.6, 0.1, and 0. And we are finished with epoch 0. But as we saw, 2 out of the 4 training samples we classified wrongly. So let's do epoch 1 and try to move towards that space of lower loss, right? That's our goal. So here again we have forward pass. The first one is classified properly. The second one we get 0.1, which is translated into 1 net activation to output, which is wrong. We update again weight minus learning rate multiplied by outputs minus target multiplied by x, which here is 0, 1, and the bias is always 1, and we get the new values. We keep doing that. Here we see that 3 out of 4 we classify wrongly, which might look worse, but I assure you that we are descending through the space which is with lesser loss. Okay, let's go ahead. We have epoch 2. In epoch 2 we classify first 2 are proper, the second ones are not. We go to epoch 3, epoch 4, epoch 5, 2 updates again, epoch 6, and we do only 1 update. So here now our weight 1 is 1.1, our weight 2 is 1.1, and our bias is minus 1. We get minus 1, which is translated into 0. Here we get 0.1 again, which is translated into 1. We update, and our new weights, and we'll see our final weights, are 1.1 for weight 1, weight 2 is 0.6, and the bias is minus 1.5. And if you observe that, it's very interesting, because see that if we combine weight 1 and weight 2, we get 1.7, which is more than 1.5. But in the same time, each of weight 1 and weight 2 is less than the bias, which is exactly what we expected. If you remember back to introduction, what we said, right? We added the bias so we can have a threshold and the neuron can, not be firing all the time. Now, if we have 1 on either input, or we don't have 1 at all, we'll get just weight 1.1 or 0.6, which will be translated to 0. But if we get both of those combined, we'll get 1. And if we quickly go back to here, we can observe the same thing, right? So we need our bias to move our decision boundary far enough from the origin in order to have all of these three as zeros and only this one as 1, which means that the bias needs to be quite a lot negative, right? And in the same time, the weights though, when we add those together, they need to be bigger than this distance in order to get a 1 here. And this is exactly what we observe. And we can see that when we go into epoch 7, we get a convergence, because when we take each of the input samples, we always get the target we want, and we learned our model and our perceptron is working. And we are ready. I hope that you enjoyed this machine learning tutorial and you got insight on the theory, and not only the theory but where it comes from, how it's connected to the biological neuron, and then exactly how the algorithm works. In our next tutorial, I will be showing a Python code implementation of the perceptron. I will be running both AND and XOR, I believe, and also a few more complicated patterns, and see how the perceptron is learning. So it's going to be very cool. I hope you enjoyed that. Make sure to subscribe, check out my other videos on Entiversal. There is a lot to look at and learn. Make sure to comment down into the description if you maybe missed on something, if I didn't make something clear enough, or you just want to have a conversation with me. Thank you for listening, and see you next time.